Hello everyone, my name is Abel Souza. I'm a recent graduate student in the Department of Computing Science at Umeå University. Today I'm going to present ASA, the Adaptive Scheduling Architecture. Other researchers also participate in these papers and they are Kristiaan Pelckmans, Devarshi Ghoshal, Lavanya Ramakrishnan and Johan Tordsson. Scientific workflows are increasingly being used in high-performance computing, or HPC systems. They support many scientific experiments where data come from different sensors and sources such as real-time streaming. In the figure in the middle, we have a direct acyclic graph, or a DAG, and it represents a scientific workflow. Each column in this DAG represents a processing phase, or stage of a scientific application. The computational tasks in a scientific workflow can be decomposed by multiple jobs, and each has varying resource needs such as number of processors. For example, a parallel region is expressed by the multiple green nodes in the DAG and can use multiple processors. Sequential regions, on the other hand, can use only one processor and are represented by single nodes. In HPC, users go through a batch queue where they submit their jobs and have to wait for resources so application can start execution. Workflow management systems are user APIs and libraries that handle the execution of a workflow. These systems usually submit jobs in two ways. One strategy is to use big jobs, sometimes also called pilot jobs. In this strategy, the maximum amount of resources that will ever be needed at runtime are allocated for the whole duration of the workflow. The second strategy is when the user, or the workflow management system, uses a per-stage submission, sometimes also called chain jobs. In this strategy, the exact amount of resources are allocated for a given stage according to its needs. In here, we illustrate how each submission strategy impacts a workflow in terms of its resource usage, usually calculated as core hours, which is the job requested time multiplied by the total number of allocated resources, such as number of requested processors. As it can be seen in the upper figure, in the big job strategy, a workflow may have a high total resource usage. This is because sequential stages are intrinsically incapable of using more than one resource, idling all the other allocated processors. An exception might happen perhaps when a workflow has only one stage. The big job strategy may lead to a lower total workflow make span because the job goes through the batch queue only once. However, as the example shows, it allocates resources in a worst-case setting. On the lower figure, in the per-stage strategy, a workflow is allocated only with as many resources as needed following each stage. The change on the amount of resource happens at the end of each stage. In this strategy, the workflow fares the most optimal resource usage, but it may end up with higher workflow make spans, which is the summation of all stage run times plus all the additional interstage queue waiting times that happen during the workflow execution. To combine the optimal total workflow resource usage in the per-stage strategy, together with the lower make spans of big jobs, we propose ASA, the Adaptive Scheduling Architecture. ASA is an architecture that transparently abstracts the management of resources provided to applications through lower-level resource managers like Slurm. By integrating with Mesos, ASA provides scientific applications with fault tolerance, resource isolation and control, besides elasticity. It also enables users to access their own scheduling strategies. All of these capabilities are available to users as a library that can be loaded at runtime and do not request any administrative privilege to be used. Together with the architecture, we also propose a proactive reinforcement learning scheduling algorithm. This algorithm estimates the behavior of the queue according to each stage in a workflow. In this way, ASA can submit jobs for an upcoming stage during the execution of a current stage and potentially reduce the workflow make span, besides achieving lower resource usage when compared to the high fares of the big job strategy. As mentioned, ASA works during the execution of a workflow stage. At runtime, ASA checks its batch queue information for an upcoming stage. It keeps a probability distribution vector and describes all possible waiting times for a given job geometry, and then samples a waiting time according to this distribution. To evaluate how well estimations are, ASA uses a loss function that updates the probability of a waiting time to be sampled. These loss functions decrease or increase this probability according to how far or how close from the real waiting time the estimated waiting time is. In this way, ASA is able to adapt itself to changes in the queue. However, in case a resource allocation is ready for use before it's actually needed, ASA releases such allocation, updates its job's internal probability estimations, and submits a new allocation request following its updated information. This resubmission process might incur in some additional resource expenditure, as we will see in the following slides. To evaluate ASA, we tested it in two Swedish supercomputer centers, Kebnekaise and RACKHAM. Both systems are well supported and run Slurm. We executed three real workflows: MONTAGE, an ASA workflow composed of four main stages; BLAST, a bioinformatics workflow composed of two main stages; and Statistics, a workflow calculating various metrics from a large dataset composed of four stages. We compare ASA to big job and per stage strategies. We record the total make span, the average resource usage in core hours, the average waiting time, the hit and miss ratios, and the average overheads. The miss ratio calculates when jobs need to be submitted again, and occurs when large estimations that the actual waiting time happens. It's exposed through the average overhead and calculated as additional core hours. Finally, in Kebnekaise, we repeated the workflow execution for 60 times, with up to 112 cores and the same number of repetitions in RACKHAM, but using 106, 320, and 640 cores. In here, we show RACKHAM results for the statistics workflow. We can see that for large core allocations, the use of ASA resulted in smaller total make spans than both per stage and big job strategies. This happens because the big job strategy has a waiting time that is higher than all of the perceived waiting times that ASA experiences. Reduced perceived waiting times are mainly due to ASA's proactive submission system that happens during the execution of a current workflow stage, and minimize the total perceived waiting times for the workflow. Besides that, since ASA learns the behavior of the batch queue during all submissions and also dynamically at one time, it can improve its estimation very quickly. In here, we have ASA results for the 60 workflow repetitions for MONTAGE, BLAST, and Statistics in both Kebnekaise and RACKHAM. We can see that ASA estimations varied more in Kebnekaise than in RACKHAM. This is more notable in submissions of 28 cores, regardless of the workflow, and results in some overhead losses. Also, because 28 cores is the queue which receives most of the interactive, debugging, and testing applications, and results in an extreme number of jobs being submitted, with all of them starting and finishing at very random times. We can see in Kebnekaise that as the allocation size increases, the variation in the workload decreases, and as estimations improve, and results in higher hit ratios and lower perceived waiting times. In RACKHAM, where workflows use more than 160 cores, this behavior is not seen, and thus achieves 100% hit ratios in all submissions with no overheads. Compared to the real waiting time, the perceived waiting time reductions are notable, and thus is able to reduce the total workflow make spans quite dramatically. By integrating the overheads experienced by ASA, in here we show a combined average resource usage for all workflows comparing the three strategies. We can see that big jobs fared almost as much as twice of what both per stage and ASA strategies fared. However, as we saw in the previous slides, ASA is able to reduce the perceived waiting times with lower make spans than both big job and per stage strategies, and results in a near optimal combination of these two strategies. To conclude, we show that ASA combines outcomes from both per stage and big job. A proactive scheduler that together with its reinforcement learning algorithm results in negligible overheads and lower total make spans. ASA benefits large queues due to the lower workload variability in these partitions, and it also performs well in smaller queues where low overheads due to resubmissions were reported. Future work points to the design of even more complex scheduling strategies where ASA's fine-grained resource control can be used to achieve higher data center throughput. Thank you very much.